All right, we're taking a look at practice question set 2A that you guys did over the weekend and submitted online for me. Starting with question number 1, easy one to start off with, I think. The physical quantity that has the same unit as impulse would be momentum, right? Because momentum, impulse, sorry, is just the change in momentum. So, of course, they're going to have the same units. The answer would be D. Number 2 says airbags are designed to deploy when a car moving at a minimum speed of 18 kilometers per hour comes to a crashing stop. The impact sensor, also moving at 18 kilometers per hour, because of course it's moving with the car, consists of a steel ball of 0.05 kilograms, which is held in position by a magnet. You can see that's the case right there, right? The steel ball, not very round, it looks more like a meteorite or something, but held in position by a magnet. On impact, the ball breaks free in 1/1000th of a second, slides within a cylinder, and as it slides down the cylinder, what happens is it connects both ends of those terminals, completes a circuit, and inflates the airbag. The airbag, we call it an airbag, but it's not really air, right? It's some gas that when an electric current goes through it ends up, sorry, some powder that when an electric current goes through ends up forming a gas really, really, really quickly so that it's inflated long before your head ever actually makes contact with it. So it's not air, it's some other kind of gas bag, but we call it an airbag. What is the magnitude of the force required to break away from the magnet? Well, I see force and I see time. When I see force and time, I typically think impulse. That's my go-to thing. Of course, F is equal to m times a will still work because really that's all impulse is, right? We derive the impulse equation from F is equal to m times a. But usually this is what ends up being the most efficient way of dealing with it. F times delta t is equal to m times delta v. Here we're looking for force, so we rearrange to solve for that. The mass of this sensor is 0, or the steel ball, I should say, is 0.050 kilograms. Delta V would be 0 minus 18 kilometers per hour. We got to convert that to meters per second. I should have circled that when I read that. I think that works out to be 5, wasn't it? 5 meters per second. We divide that by the time of 1 times 10 to the negative 3 seconds. And I think when we did that, it worked out to be C, I think it was, wasn't it? 2.5 times 10 to the 2 newtons. So really what we're saying here is that if you're in a crash, it takes 250 newtons to break this ball free. In other words, it takes 250 newtons in order to activate this airbag. Hey, why don't we just activate it as soon as there's any crash? Well, because it doesn't make sense, right? If a shopping cart hits your car in the parking lot of Walmart, well, you don't want your airbag to go off. It costs you like $1,000 to get your airbag repacked. Okay? You don't want to do that every time there's a slightest little bump on your car. You don't need an airbag for tiny little collisions. We want a bigger force in order to activate the airbag. Okay? 3, if the car was moving at 18 kilometers per hour, what's the maximum speed of the ball immediately after impact? How fast could the ball possibly be moving after impact if it was moving at 18 kilometers per hour before impact? 18 kilometers per hour, which is 5 meters per second. Good. So don't make that one harder than it has to be, right? 4, if the car was initially moving at 18, the driver had a mass of 70, and the airbag stopped him in 0.1 seconds. The magnitude of the force on a driver during the deceleration would be what? Once again, we're dealing with a time and a force, so I'm thinking impulse. I'm going to say F times delta T is equal to M times delta V. Almost the same as a couple questions ago here, question number 2, except this time we got a different mass. We're going to say, 70 times delta V, which is 0 minus 18, divided by the time interval, which is 0.1 seconds. I don't remember what that was. We get 3.5 times 10 to the 3 newtons. So 3,500 newtons is the force on the driver. You're going to learn later today. We alluded to this here the other day when we did our egg drop experiment. The idea that when we're stopping an object, we usually want to increase the stopping time to decrease the force. You're going to find later on today that if we were to um, increase the time of contact with the airbag, then let's say double it, which would be a huge boost in the technology of an airbag. If you could double the stopping time, that would reduce the force by a factor of 2. So it would end up being about 1,750 newtons acting on the driver, which would obviously lead to less chance of injury. We'll see why that's the case a little bit later on. 5, during this entire process from impact to airbag inflation takes less than 3 times 10 to the negative 3 seconds. During the same time, how far forward would a passenger who was not wearing a seatbelt move? So we got the driver not wearing, or a passenger not wearing a seatbelt. Um, the airbag takes 3 times 10 to the negative 3 seconds to inflate. So we better hope that we don't hit it before it's inflated, right? We better hope we don't move that far forward, far enough forward in order to hit the airbag before it inflates. We want to know how far forward we will move before the airbag is actually inflated. So we're going to say just V is equal to delta D over delta T, and D is equal to V times T. The driver of the car is going to continue moving at 5 meters per second. That's how fast the car was moving, 15 kilometers per hour or 18 kilometers per hour, 5 meters per second for 3 times 10 to the negative 3 seconds. I think it gives me 1.5 times 10 to the negative 2 meters. So how far forward does the driver move before the airbag is inflated? 1.5 centimeters. That's how fast this thing actually inflates. In fact, this all happens so quickly. If you've ever been in the car with an airbag going off, you'll know this. If not, maybe you don't know this. There's holes all around the airbag. So it actually it puts so much pressure into the bag that it inflates despite the holes. But then once the chemical reaction is over, it actually deflates. So it's actually in the process of deflating by the time your head ever actually makes contact with it. Anybody want to throw that out at me why that might be the case? We want to take a guess at why we would want the airbag to be deflating by the time your head actually hits it? To cushion your head even more, right? That increases the stopping time even more. The nature of the airbag, right? The air inside it or the gas inside it increases the stopping time of your head somewhat over a steering wheel. But the fact that it's deflating is kind of like cradling a baseball, right? By moving your hand back a little bit, or a basketball by moving your hands back a little bit as you're catching it. Increases stopping time even more. Okay, we're good there?